It's amazing to me how that happens. All right, voice. Alrighty, folks. I'm still dealing with the camera issue, so I can turn the camera on. You can see something. There we go. This is a clear nose skate sitting on my desk. See, that's why it's called a clear nose skate. Skates are why is that doing that? Oh, there we go. Skates are related to sharks and rays, and stingrays and that sort of stuff. Skates are a little different than most sharks because they lay eggs, whereas a lot of sharks give birth to live young. But this is one that's in a jar on my desk. So at least got something interesting to show you, I suppose. But I won't leave the video on because I don't know if you want to stare at a fish in a bottle. I guess I didn't share the video. Yeah, here we go. I'm gonna do that. There we go. Now it is. Now you can see the skate. See, it's called a clear nose skate. Sorry if I'm making you motion sickness. Why is that? There we go. It's like you have to turn the camera opposite. There we go. Okay. But unfortunately, again, the camera in the front is not working, so you can't see me. And I'm still looking to try and figure out why that is. I love how these programs, how they update them and make them, oh, it's new, it's better. And I'm like, yeah, but you messed something up. Something's wrong with the video part. So, all right, I do have the recording started. So let me go ahead and get some announcements out of the way. Remember, first of all, Monday, of course, we don't have class because it is Martin Luther King Day. So the next time we meet for class, we'll be again online on Tuesdays. And then Wednesdays, of course, we're in campus. And exercise 2 is the lab you'll be doing. So make sure you download that. And that's up on Blackboard and ready to be downloaded. So do be sure you have a copy of that. Keep in mind, again, with this being the summer semester, with this being a short semester like the summer, things move along pretty quickly. So don't lose track of time. Take a look at the syllabus. We have next week, right? We're basically Tuesday, Wednesday, and Thursday. Then the following Monday, we take our first exam. So you should start studying now. If I were you, I wouldn't wait till the last minute. This course has a lot of content to it, a lot of information. And if your mode of studying was the old stay up all night, drink coffee, and cram it all in, that's going to be rough with this class. There's just a lot of information. I'm not sure that that's going to be the most effective way to study. So when I say you should start studying now, I'm not saying that you should sit down every night for 2 or 3 hours and look over your information. But like, for example, I would flip through my notes and just kind of always keep myself sort of present in the moment of the material that we're talking about. It's always best to, right before class each day, to kind of look at where we were, kind of review your notes, your textbook again, to kind of give us an idea as we make this a big picture, which is what I'm trying to do, is combine this all together. Okay, so I have some people always say, do you have any tricks about studying for your exams? I really don't have any tricks about studying for my exams. I do have some techniques that I used as a student that helping study for just exams in general. One of them that I was telling, but it's kind of a simple thing, and it seems like, why does that work? Maybe as much of it was placebo as anything, but before an exam, I would always read the material over that I was going to have the exam over, my notes, my text, whatever the case may be. And I would do that at the last thing in the evening, right? So I would, maybe as you're sitting in bed, now this wouldn't work for me now because like I said, I immediately fall asleep. But if you're laying in bed, right before you turn the light out, right before you go to sleep, look over your information, look over your notes, do a scan of the information. And then as we're getting closer to the exam time, try doing that first thing in the morning too. Set your alarm for, I don't know, half hour earlier, 15 minutes earlier. Get up, get your coffee, and then again, look at your notes. So the point is, the information is the last thing you see at night before you go to sleep. It's the first thing you see in the morning. I have no idea if there's any psychological evidence to suggest that that works, to be honest with you. All I'm telling you is it made me more comfortable in taking exams, and it helped me when I was in college. Again, it may be placebo, but as I always say about placebos, I don't care if it's a placebo if it works. If you tell me that this is really nothing more than a sugar pill, but I'm feeling better, I don't care. Doesn't matter to me one way or the other. So give that a shot. See if that helps. Now, if you have some other techniques of studying and you're doing well in school, by all means, as we said with the metric system the other day in lab, if you have a better way of doing it or a way that works for you, don't switch now. Okay, so chapter 3, excuse me, my voice is still a little bit raw. Chapter 3 is an entire chapter about water, and it seems to be kind of overblown. Why would we write an entire chapter about water when we're sitting here talking about biology? Well, I know you guys have all heard many times that the life that we know on this planet, and that's really the interesting thing for me, of course, planets with other planets with life, but life as we know it, Earth life. So what I mean is there could be other types of life, needs water. Without water, we can't survive. Life evolved in the water. Life is dependent upon the water for a variety of reasons, not just, as you'll see today, not just for drinking and staying hydrated, but for a number of other reasons. Excuse me. Water is so important for life on the planet, that we would not have the diversity of organisms that we have on Earth today without the water that we have. And if you're looking at that picture of Earth there, which I've hopefully recognize that as being Earth, you realize that when you look at it, we're a big blue marble, right? Isn't that what Carl Sagan said, the astronomer? A big blue marble, I believe he called us, because when you look at Earth, it's really mostly water, right? There was this push a number of years ago. Folks tried to get the Earth renamed into, let me type it. Oh, I spelled it wrong. They tried to get it renamed to Oceanus, okay? To indicate that really most of the Earth is not Earth, what we call the terrestrial, it's mostly water. So doggone it, with water covering 2/3, 3/4 of the planet, with your body made up of about the same amount of proportion of water, we're going to have to dig into this and find out why it's so important. I mean, when it's found everywhere and when it's crucial for life, there must be something about that relatively simple substance, right? Just two hydrogens and an oxygen sharing those electrons, not sharing them equally, remember, but sharing those electrons. There must be something about those substances that make water very unique and important. So let's get into that now. Let's do that first by stepping back for a moment to the other day, yesterday actually, when we were talking about bonds. Remember I said that there were, we discussed three types of bonds. We discussed the ionic bond, which occurs between charged atoms when you give up an electron and accept an electron. We discussed a covalent bond, right, where the word literally means to share electrons. Remember, valent shells, valent electrons is all dealing with those electrons in the outer shell. So in a covalent bond, atoms get together and form a bond because they're sharing electrons. They can share a pair or two pair, even up to 3 pair of electrons, right? The other type of bond that I talked about, and I told you at the time, it was the weakest of all the bonds. Very weak bond, very easy to break. I showed you in class tipping the bottle of water, right? So they tip the bottle of water up, there's water left in the bottle, water went down the sink, and the bond was broke between when I tipped the bottle up. Very easy to break. You didn't see me struggling to break a hydrogen bond. Hydrogen bonds are like weak magnetic bonds. And hydrogen bonds occur, hopefully you remember, because in a molecule, one of the atoms is a pig. And what I mean by pig, it's a pig for electrons. It does not like to share those electrons equally. In this case, in the water, it's oxygen, right? Oxygen shares a pair of electrons with each of those hydrogens. Look at the picture in the middle. I'm sorry I left my pen at home too, but maybe I can draw with my finger. See there, there. Look at that picture right there in the middle. How can I make the statement that oxygen is sharing one pair of electrons with each of those hydrogens? What in that picture tells me all of what I just said, that electrons are being shared and how many are being shared. That's right. That's right, Raymond. It's the line. The line is the symbology that we use in chemistry that indicates that between those oxygens and those hydrogens, it is a covalent bond, right? Recall, I told you in class that you would never write this compound this way. You would never put the line in between sodium and chlorine because, remember, that's not a covalent bond. Trying to erase it. But anyway, it would be typically written like this, although sometimes I said you will see it written where they put the charge in there, right? The positives and the minuses. Hello, I need to make a minus. Why is that making a minus for me? There we go, right? So in an ionic bond, it's two things that are basically magnetic, right? Electromagnetic attraction to one another. And there was one other bond that occurred this sort of magnetic thing. But you got to be careful. And I mentioned this in class. Don't confuse ionic bonds with positive and negative sticking together with a hydrogen bond. Ionic bonds occur between ions. They occur between atoms. Hydrogen bonds occur between molecules, right? Don't forget that. It's an easy mistake. I've seen students do it time and time again in an exam. I ask them to describe ionic bonds, and I get maybe some ionic bond stuff, and then I get some hydrogen bond stuff. That's not an ionic bond. And remember, of course, the reason why water molecules are able to make those hydrogen bonds is because of that doggone oxygen again. When oxygen sucks up those electrons or keeps them for themselves most of the time. Good morning, ladies. When it keeps it for themselves most of the time, that means the molecule of water ends up taking on net poles, net positive or net negative. So the hydrogen ends become net positive and the oxygen ends become net negative. Does anybody remember why the oxygen end of the molecule becomes a net negative charge? What was the explanation I gave you in class? Good morning. Good morning. How you two doing? How's your dog? I confirmed our conversation with an A&P instructor the other day, and they said the same thing, that yes, indeed, with heavy fiber, it should sink. But perhaps the other dog is eating something else out in the yard, maybe. Now, this was an A&P instructor, not a vet. Doesn't gain electrons, Tim. Be careful with that word gain. When we use the word gain and loss, we usually use those for ionic. We're not. Yeah. The atomic number is heavier on one side. Okay, Raymond, you got the right idea, right? The atomic number of oxygen is 8, right? Again, you don't have to memorize that. So it's in its pure form, oxygen has 8 positives and 8 negatives balancing each other out. Yeah, but like, what was it, Raymond, who said about the atomic number being heavier on one side? What basically happens is, since the hydrogens spend most of their time down around the oxygen, that many times, or a higher proportion of the time, you got 8 positives trying to balance out 9 or even 10 negatives, right? It could balance, try to balance maybe one of the electrons from one of the hydrogens, because maybe that electron at that time is around one of the hydrogens, or if both of those electrons were around the oxygen, you would have that imbalance, right? So what that ends up doing is it makes the molecule polar, right? And we talked about covalent bonds. Covalent bonds can be polar or they can be nonpolar. If those electrons are being shared equally, like often happens between 2 carbon atoms, there we go, that's going to be a nonpolar covalent bond. I'm sorry, it's supposed to be a C. Can't draw with my finger as well. All right, so that's 2 carbon atoms. So that's a nonpolar covalent bond. That means the electrons are being shared equally. You're not going to find positive and negative ends on that molecule. It's only with specialized molecules, typically water, but remember I showed you could also be with ammonia. Ammonia is the nitrogen and the 3 hydrogens, right? And the same thing, nitrogen is like the oxygen. Again, the electrons it shares with those 3 hydrogens are going to spend most of the time up around the nitrogen end, okay? All right, now, then a hydrogen bond results only if you have polar covalently bonded molecules, okay? You cannot get a hydrogen bond between things that are nonpolar. Nonpolar things don't have positive and negative things to stick them together. Only polar things do. So when you stick a bunch of these polar covalently bonded molecules together, like we see in the picture here, they're going to stick to one another, aren't they? That's what the little dashed lines mean. See the positives and the negatives? Now, of course, since those electrons are all moving around, these bonds are breaking and reforming, continually. But since the electrons, because of oxygen's, demand for those electrons, if you will, because of that, we know that most of the time we're going to have this polar covalent molecule, and those molecules are going to be held together slightly by those hydrogen bonds, right? So that's the chemistry behind it. Any questions on that? Because I'm going to stick with water, and we're going to talk a lot more about those hydrogen bonds, because even though they're really weak, that's what I love about this, man. I tell you, if water didn't form these hydrogen bonds, we wouldn't be here talking about it. Isn't that amazing? When you look at that, you think about some, not trick, but some property of chemistry allows you and I and everything else on the planet to evolve the way we did. I just never grow tired of just being fascinated by that. Okay, so no questions about hydrogen bonds and about water molecules and polar covalent, huh? We're all set? Okay, now let's do the chemistry to the biology thing, right? That's what I've been trying to do. We talked about in lab. We talked about the chemistry. Remember, we measured those blocks of wood, and the exercise wasn't to measure blocks of wood. The exercise was to help you mathematically understand why the smaller block of wood had the greater surface area to volume ratio, right? Smaller block of wood had the greater surface area to volume ratio, and I said yesterday that we will talk more about that when we get into cells in chapter 6. So we're going to do the same thing here. We're going to take the chemistry that we understand about hydrogen bonds and relate it to what living organisms can do because of that. Right? I don't think this table is in your book. I think I borrowed this from another book. I might have borrowed it from y'all's. I can't remember exactly. If it's not in your book, let me look and see if it's in your book. Is it in your book? Is this table in your book? Let's see where throughout the years, I have accumulated lecture slides. I see one. I'm like, oh, I like that one better, so I use that one. And then sometimes I forget where they've come from. But regardless if it's not in your book that way, the information that's in it is in your book. Yeah, that table I must have got from someplace else. Nonetheless, all right, let's look at the properties of water. First of all, number one, water is cohesive, okay? What does it mean for something to be cohesive? Oh, that's a good idea. Yeah, it sticks together. So water molecules stick together. Okay, now, do you know why they stick together? If someone asked you, the water property of cohesion, how does that happen? What would you tell them? Without reading the explanation where the answer is, obviously, in that table. Would you be able to tell them that? Would you understand that the cohesion of water molecules is because of the fact that they're polar? Yeah. Yeah, because you create a molecule that has positive and negative ends, and they stick together. They cohese. Is that a word? Anyway, they exhibit cohesion. Okay, so what is that good for living organisms, right? Now, I'm going to come back to this slide, so don't worry when I switch off of it, because I'm going to use this as a central slide and then kind of move into each particular property with some other slides. So I will come back to this, all right? So talking about cohesion. Why is that good for living things? Cohesion is the chemical property. How do living things use that? Remember what I've said, I'm sure a couple of times already, and I will say more and more. Those laws of physics and laws of chemistry were already in place when living things came on the scene. So we have to obey those laws of chemistry and physics. So what we're doing is obeying those laws, and in some cases, we're using the chemistry to help us survive. Maybe you might say to our advantage. So water molecules sticking together. You noticed that yesterday. You saw a direct evidence of the cohesion of water molecules yesterday in lab, didn't you? Do you remember what did you do in lab, or what did you observe in lab? I remember one of you made a comment about it too, a very good comment about it. What did you do in lab that indicated that water molecules stick to things? Yeah, the glass, right, of the graduated cylinder. Remember the meniscus that forms? Sorry, I don't know why that drew that way, but anyway, the meniscus that forms, right? Stop. Oh, what's going on? Oh my goodness, my computer's gone crazy. There we go. The meniscus that forms it. Yeah, that's okay. The water, the glass in the graduated cylinder is also sticky. It also has those positive and negative ends, so it pulls the water molecule up the side. You understand, of course, the meniscus is a three-dimensional. So if you're looking down on it, it's a bowl that's been pulled up. It's not just, I'm sure you understand. I just want to make sure. Okay, so for living things, how about if you're a tree? Cohesive water molecules would be really beneficial because as we're going to learn in, I don't remember, chapter 7 or 8 or wherever photosynthesis is, leaves need water for photosynthesis. Well, they also need water for other things. They're living things and they can't be dehydrated. But as far as photosynthesis goes, that occurs up in the leaves. It doesn't occur in the roots, doesn't occur in the trunk. It only occurs in things that are green. Photosynthesis needs a molecule. It needs a pigment molecule. We'll talk about this later on. I mentioned to you yesterday when we were saying about that movie 2010 where they chlorophyll. Okay, chlorophyll is green. I always tell folks, sometimes I wonder, or sometimes I wish I could photosynthesize. Think how easy that would be. You know, if you're in a rush between school and work and you ain't got time to pull in to get something to eat and hang your arm out the window, absorb some sun, you're all set and ready to go. Wouldn't that be cool? I would love that. You have to be green, though. You have to be like Kermit the Frog. I wonder if Kermit could photosynthesize. So that would be the drawback. But I guess I would risk one arm being green. I guess I would risk one arm being green, maybe. Make it advantageous. Okay, so this cohesive of water molecules, though. If this tree is 60 feet tall, how does the water get to the very top leaves at the top of the tree? Water falls down as rain onto the ground. We all know that plants absorb water through their roots. That's why they have roots. And then if you'll notice in the direction of water movement, the arrows are going against gravity. Oh yeah, that would work. The arrows are indicating the water is being pulled up against gravity, right? Gravity works on water just like it does on everything, on you and me. It wants to pull things down towards the center of the earth. All right, so how do those water molecules get up to the top? Well, they're connected together. You see, inside of a tree, if we looked at a microscope picture, and that's what that little, whenever you see a microscope picture, folks, they oftentimes will give you a scale. So what we're saying there's that distance is 300 microns. Remember, the micron was that conversion unit way over on the right, which means that's a really, really small measurement. So this is down at the electron microscope level. And if you look, we've done a cross section through a tree. You can see that there are holes or what looks like could be tubes, right? Those are indeed tubes. They're called water conducting cells. And if you look at this picture up here, you can see them. This is under a regular microscope. I'm sorry, that's supposed to be an arrow, but you can see the tubes, right? See them there and there? That's how the water gets up to the top of the tree. That's the conduit. That's the pipe that brings it up there. But how do the water molecules deal with this problem of gravity? If you look in the little inset picture there, you notice that the water molecules will undergo adhesion to the sides of the tubes. All right, adhesion they stick to. And then since the water molecules are stuck to each other, it's kind of like, well, it's exactly like, to be honest with you, what you saw in the graduated cylinder. It's what you saw in the graduated cylinder. What chart is still up? You're not looking at a picture of a tree? Wait a minute. Okay, so Tim sees the tree. Raymond, you're seeing the table? Okay, now you see a tree? Raymond, try refreshing. I don't know what that means. I don't know why that would, yeah. Let's give Raymond a second to get back in. He just left. Yeah, that spider, isn't that cool? How many of y'all like spiders? My son can't stand him. He's definitely afraid of them. And he's a big guy. My son is 6'2". And it's funny. I found a wolf spider up in the attic one time when I was up there, and I put him in a jar, and I was chasing around the house with it. He was an adult. He wasn't a kid. But he wasn't very happy about it. He's really afraid of him. Raymond, come back in. There's Raymond. Yeah, that's cool. Raymond, how about now? Can you see the? Got it. That's weird. Maybe just try next time refreshing the screen, hitting the reload button. Maybe that'll help. Okay, so we're talking about those water molecules being pulled up those conducting cells, right? So the hydrogen bonds, that's what the little dashed lines are absolutely crucial here, aren't they? How would you get those water molecules against the force of gravity if you didn't have those water molecules sticking not only to the sides of those water conducting cells, but to each other, right? So it's like a big chain that's pulling up. And that adhesion of water molecules that occurs and the cohesion between them, cohesion is usually indicates two similar things sticking together, cohesion, so two water molecules. Adhesion would be when something sticks to something that it's not like. So water sticking to the side of the conducting cells is adhesion. Water sticking to water is cohesion. Does that make sense? Now, if you're wondering what this microscope picture in the upper right that I circled, where that comes from, what you do is you take the stem or the root of a tree and you make a cross section. So if this is the stem or the root, we've cut it this way in a very thin slice. Okay. The spider. Spider's walking on water, isn't he? Isn't that cool? Spiders, many other creatures can walk on water, but what I really want you to focus on is right at the tip of the legs of the spider. Spiders have 8 legs, right? They're not insects. Insects have 6 legs. Spiders are a special type of arthropod known as arachnids. The scorpions belong in that group too. So do our buddies, the tigers and the mites and all of those. But notice in the picture what the tips of the legs are doing to that surface of the water. Can you see that? What does it look like? What does it look like is going on there? Kind of a meniscus. There you go, Raymond. Yeah, kind of an indentation. Not weight, density. Density. Beth and Lizzie, you got to think about density. It may weigh more than a gram, but as long as its density is less than water, right? But this is a little bit of a trick. The density of that spider is greater than water. That spider should, by all other accounts, stick. But Tim said surface tension. What's surface tension? Raymond, it's not, we would only displace the volume when it's submerged. This thing is not submerged. What's surface tension, Tim? Or I guess I could just say what causes surface tension. Balance. Of course, that spider that's walking across the surface of the water is walking on water molecules, isn't it? Now, right. Surface tension is the fact that those water molecules are sticking together very slightly. Remember, I can break it just by tipping a pitcher. So while that spider should, by all other counts, the density thing should sink, the fact that those water molecules have those slight hydrogen bonds allows the water molecules on the surface, that's the surface tension thing that Tim mentioned, to give just a little bit, but not enough. Now, if that spider increased weight just a little bit more, or if the legs were a little bit bigger, then it would be too much and it would bust those hydrogen bonds and the thing would sink. But you notice if you spread your body out, right, like that spider is doing, and you just barely are resting on the surface, you can float a dime on the surface of water. Take a glass of water, and it takes a little bit of practice, but if you very gently, I did in school, I remember, if you very gently place that dime down there, it will float on the surface of the water. Now, if you just barely jiggle the glass, it'll break. But that dime floating on the surface is because of surface tension, right? You actually are taking advantage of those slight hydrogen bonds. Now, from a biological point of view, obviously the tree, the fact that water molecules stick together is important. But if you're some sort of critter like a water strider or a spider or in those other critters that can live on the surface of the water, you want that slight tension, right? You want just enough that you can walk on. Now, could we do this? Step out into your pool in your backyard and say, well, maybe the surface tension will hold it? Good question, Tim. I think it would depend. As the water got rougher and rougher, it would start to, those water molecules would be moving around and they would be breaking bonds and recreating bonds. I don't think if it got, I think there's probably an upper limit as to how rough the water could get before this wouldn't work. If you had floaties, yes, if you had floaties, that would work. That's right. If they had little tiny spider floaties. All right. Let me go back to the previous slide. Anybody got any questions for me about cohesion? Yeah, that's true. That's true. And I'll bet it is. I'll bet once you agitate the water enough, you get to a point where you make those hydrogen bonds not unstable, but the fact that they're breaking apart because the water's moving around, you probably, as a spider, couldn't take advantage of it then. All right. Back here we go. Now, the second two, high specific heat and high heat of vaporization, I kind of lump those together and in a biological sense. And if you follow the arrow down below, those two things have to do with what we call temperature moderation. And I put the seesaw in there again to remind you that temperature moderation, just like everything we've talked about, is all part of that homeostasis, right? Keeping yourself warm, keeping yourself cool, the Goldilocks thing. That's all part of temperature moderation. Very important for living organisms, right? Quite important for living organisms. Especially important for us warm-blooded organisms. So those two chemical properties of water, the fact that they have high specific heat, high heat of vaporization. Now, if you know what that means, that's great. If you don't worry about it. We're gonna talk about it. But those two things combined work together to give living things this ability to moderate their temperature, right? And we talked about you sweat because you get too warm, you shiver because you get too cold. All of that's important. Let's see how water helps do that, though. This slide over here. All right, let's get some terminology and some principles out of the way first before we start looking at how these water molecules are able to do that. First of all, water absorbs heat from warmer air and it releases stored heat to cooler air. Okay, so when it's warm outside here in Florida, the ocean around us, and being that we're on a peninsula, we got lots of ocean. The ocean around us is absorbing a lot of the heat from the sun. As a matter of fact, that's another reason why we're able to live on this earth. The amount of water we have on earth allows the temperature of the earth to stay within a reasonable range. We're 94, 93 million miles away from the sun. The sun would still be too warm for us if indeed we didn't have as much water as we do. Think about the water in your car mixed in with your radiator fluid, right? With the antifreeze. What that purpose is to absorb heat from the engine. The oceans of the world and lakes and that sort of stuff absorb heat from the sun. So the atmosphere of the earth warms up, but it doesn't warm up dramatically. We don't have these huge temperature ranges from night to day like you do on Mars. And I got some data on that. I'll show you in just a second what life is like on Mars without appreciable water. Okay, so this means that water can absorb and release a large amount of heat with only a slight change in its own temperature. Okay, now translated, it's the same adage that someone always tells you: a watched pot never boils. Or if you've ever tried to boil water in a microwave, it takes a while to do that, doesn't it? Even just boiling water on a stove, you're boiling water for spaghetti. You can't just turn on the stove and it's like, oh boy, it's ready. It's because the heat from the element, right, from the stove, or in the microwave's case, is heating up the water. Yes, it is. But water can absorb a lot of heat before it does what we say changes state. Changes state. Now, what are the 3 states of matter? 3 states of matter, folks. This is way back in science. 3 states of matter. There you go. Solid, liquid, and gas. That's what I'm talking about. So what we're saying is water will absorb a lot of heat before before it changes from liquid to gas. That's why it takes a lot of heat to boil water. That's what you're doing when you're boiling water. You're turning from a liquid into steam, into a gas. So that means water is a good regulator. Again, go back to the radiator of your car. If the liquid in the radiator of your car didn't have this ability to resist changing state. In other words, if every amount of heat it absorbed caused it to become a gas, you boil off the liquid in your radiator before you knew it, your car wouldn't work anymore. And that happens sometimes, doesn't it? So water is this great temperature regulator, right? And for us in Florida, oh my goodness, this is why we have such, well, maybe some people wouldn't call them mild summer evenings. Let's call them mild spring and autumn evenings. Because even in the summertime in the evening, if the temperature goes down, it's still humid as hell. But that's because all of the ocean around us during the day is absorbing the heat from the sun. And at night, when the sun goes down, and the atmosphere is no longer being heated by the sun, guess what the ocean does? The heat from the ocean radiates back up into the air. So the temperature at night, in spite of the fact that we don't have sunlight to keep us warm, is regulated, modified somewhat by the heat that's released from the water. And being that we live on a peninsula surrounded on 3 sides, that's a very big effect on us. Yeah, sure does, doesn't it? Right? Okay, and like I said, in a couple of slides, I'll show you some data from Mars, and we can compare and contrast Mars in terms of its temperature extremes, and keeping in fact that Mars has little or no water. Yep, that's a lot to do with it. I grew up in West Texas. I grew up in El Paso, Texas. You've never heard of it, you're not missing anything. But El Paso, Texas is out in the middle of the desert. And at night, even in the summertime, people would be out hiking in the desert or doing something in the desert, and they get lost. And even in the summertime, people would sometimes die of hypothermia in the evening. The reason why that is in the desert, there's very little moisture in the air, right? There's very little water vapor. So there's very little to stop the heat that's coming out of the ground, because the ground absorbs heat from the sun just like the water does, from radiating out into space. So deserts at night cool off very quickly. Very quick, and can become dangerously cool even when during the day it's blistering hot. So think about that next time you're out there wandering around the desert. Okay, what do we mean by water's high specific heat? That's what I've been talking about. I put it in parentheses for you. The specific heat is the amount of heat that water must absorb or lose for 1 gram to change its temperature 1 degree Celsius. Now, if you're thinking, what's the 1 gram and the 1 degree Celsius? It's a standard. All right. Remember how we were talking about the weight of protons? And I said protons weigh, something. They weigh a really small portion of a gram. And instead of using those really small numbers, we have another measurement unit. We call it the atomic mass unit, or sometimes it's called a Dalton. Right? Dalton was a fellow years ago who made the proclamation that he believes everything is made up of atoms and molecules. We know that now, but back then that was significant. And he did some other work as well. And in honor of him, we call that measurement of unit a Dalton. So a proton, you say, is the standard. A proton weighs 1 Dalton. And since a neutron weighs the same as a proton, it also weighs 1 Dalton. Remember, electrons, the weight is, we don't really worry about that too much. So it's the same thing with specific heat. Specific heat is for any substance, okay, no matter what it is the amount of heat that's going to take to raise or lower the temperature, right? The amount of heat that's absorbed or lost over 1 gram of that substance by only 1 degree. All right. So water, we call that specific heat. We give that a measurement called a calorie. Okay. And the amount of heat it takes to raise 1 gram of water 1 degree Celsius is 1 calorie. See, I wrote down below. The amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius is called a calorie. Now, how many of y'all knew that that's what a calorie really was, and how many of you just thought it had something to do with food? Yeah. If you had chemistry or physics classes, you might have learned about that. The reason why the terms are used in food is because what we're basically saying here is calorie is an amount of energy. So food has energy in it, and we can rate that as calories. So basically what they say is if you say a hamburger has 400 calories, we could take that hamburger and we could heat up 400 grams of water 1 degree Celsius. We could burn that hamburger, flames, and put a pot over top and put 1 gram of water and 1 calorie coming out, well, because 400 calories in a hamburger, we could do it to 400 grams of water and raise it 1 degree Celsius. Kinda. Same idea. Yeah. As a matter of fact, that's how they figure out calories in food. You ever wonder when you open up 310 calories per serving, they put it into something called a, let me type it because it's called a BOM. Oh, shoot. Spell BOM, Steve. BOM. A BOM calorimeter. What a BOM calorimeter is, you put the food into this device, you burn it up, that's the BOM part, and the device reads how much heat was given off, and that tells you how many calories it is. Now, interestingly enough, a calorie is 1 gram of water raising 1 degree Celsius. The calories in food, for sake of simplicity, we call them calories, but the calories that you see in the food are actually kilocalories. So that 350 calorie serving actually has 350,000 calories. Right? So if you're watching your caloric intake to 1,000 calories a day, you're actually eating 100,000 calories. Oh, wait a minute. No. 1 million calories. Excuse me. There's that math thing again. That's something. So that 1 calorie diet drink, how many calories in a 1 calorie diet drink? How many real calories in a 1 calorie diet drink? Yeah. It's all relative though, right? I mean, it doesn't mean, oh my goodness, how many calories we're eating, because we're basing it all on kilocalories. We're just leaving off the kilo because it's easier to tell people about calories rather than kilocalories, okay? All right, so the big thing here, of course, that I'm focusing, and I want to make sure that we stay on track here with what's in the arrow, water resists changing temperature and state. So water has a tendency to want to stay a liquid. Want to stay a liquid. All right, now, why that is? I bet you know. Why that is because of hydrogen bonds. All right, now, what I've done here is I've replaced the hydrogen bonds with springs, and I'm going to show you why I did the springs here in just a second. Okay, so these are a bunch of hydrogen bonds. The springs are representing these are a bunch of water molecules. The springs are representing the hydrogen bonds, and hold on, I'm on the wrong. Oh, there I am. Okay, and I want to show you what happens. So water molecules, when they heat up, they're absorbing energy, and I'm saying they absorb energy without changing state. All right, so the water can stay a liquid. Now, life needs liquid water. We can't live off gaseous water. You can't drink a glass of steam and have it, you'd be a little hot, and have it deal with your thirst. It won't work that way. So it's liquid water. So for living things, we're trying to, we're taking advantage of the fact that water wants to stay a liquid, and it's because of those springs. As you heat water up, as you heat up anything, molecules start moving faster. I'm sure you're aware of this. You probably heard that in school. As we heat up the environment, the molecules in that environment, the atoms in that environment, everything in that environment moves more quickly. This will become important again when we talk about enzymes, by the way. All right, so what we say is the molecules are bouncing around more the more you heat them up. So in the case of a water molecule, oh, it didn't do it. I got it to do it earlier. I thought that if I made it click on my PowerPoint, it would do it on Collaborate. But anyway, what I was trying to show you is as those water molecules are absorbing heat, those springs are going to start bouncing. All right, so those water molecules are going to bounce back and forth on those springs. Now, considering they're connected with the spring, they're not going to disconnect. All right, they're going to bounce. And as you add more heat, they're going to bounce more. Now, if you get it hot enough, okay, if you start it to change state, then those springs, those hydrogen bonds are going to break. The water molecules are going to move further apart from one another, and they're no longer going to be a liquid. They're going to be a gas. You see, 3 states of matter, solid, liquid, and gas, are dependent on density. Things with high density are solids, medium densities are liquids, things with low densities are gases. So when you take liquid water with a medium density and you heat it up to the point where these springs are bouncing, 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 and all of a sudden they start breaking because you've got so much heat, because they're just bouncing so dramatically, and they start going off into space as steam, what you've done is you've changed state. All right, you've decreased the density, you've changed state, you've made it a gas. All right, now the reason why water can absorb so much heat before that happens, the reason why water can minimize temperature fluctuations, the reason why it can kind of keep us in that Goldilocks and maintain that homeostasis, the reason why it takes forever to boil that water on a stove or in a microwave is you have to heat it up to the point where you start to break the springs. That's when you turn it into gas. And those springs can bounce a lot before that happens. So the energy that would normally take any other substance and cause it to turn into a gas, that energy is being absorbed in part by those springs. Those springs are bouncing, bouncing, bouncing. And how do they get? The more they bounce, the more they bounce. I wish I had my camera there. Oh, I don't. Anyway, bouncing, 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 bouncing back and forth. And then they bounce and they bounce and they bounce. And they get hot. And all of a sudden, the springs break. They come apart. And now we're a gas. Yeah, there you go. You got it exactly right. That's what's happening. On the stove, the water is heating up. The springs are bouncing, 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 and then when they start to boil, the water at the surface specifically, the hydrogen bonds break, and those water molecules drift off into the atmosphere and become steam, right? So from a living organism, though, what this means, right, is the fact that water is a good moderator. So if you walk outside into the side onto the asphalt in the middle of August here in Florida, where it's a nice comfortable 700 degrees, right? It's hot, right? You're not going to boil. Your body is not going to suffer the ill effects of heat because the water in your body is absorbing the heat. The heat's not going to your body. It's not affecting important organs. Now, you get too hot, it will. Don't get me wrong. But before that happens, you can deal with that because these springs are bouncing, and that's where the heat is going. That's where the potentially damaging heat is going. That's where the energy is going, right? So you can live in these kinds of conditions and not have to worry about being too hot, right? Assuming, of course, that you're hydrated enough and the other conditions are met. Without having to worry about getting too warm. So it's a good temperature moderator for us, right? Let me show you what it would be like on Mars if we didn't have water. Now, I know I'm going from organism to planetary back to organism, but think about a planet in this context as being kind of like an organism. Just like Earth is kind of like a superorganism, right? It survives because of all the water, which allows the temperatures to be regulated, and life can then survive. Let's see what it's like on Mars, though. Mars is different. Mars may have had water at one time, but here's your average temperature range on Mars. Mars is in the upper left. During the day in the afternoon, it rises to a balmy 0 degrees Celsius, freezing. And at night, you might need a sweater, right? Minus 103 Fahrenheit, minus 75 Celsius. Okay, now, I know Mars is a little bit further away from the sun, so it wouldn't be quite as hot as us. That's no doubt about that. But the big reason why we have these wide temperature range extremes on Mars is because of the fact that you don't have water regulating. So during the day when the sun is facing, during the day when that part of the planet is facing the sun, all of that heat, all from the sun, is being absorbed into those rocks. Okay, and then at night, since there's no water to kind of release the heat back to moderate, all that heat from the rocks and from the terrestrial part goes off into space, and it gets friggin' cold, right? Minus 103. Elton John wrote about it in Rocket Man. It's no place to raise your kid. In fact, it's cold as hell. Oh, only at one time. You know what I always thought? If you're going to live on Mars, you would have to live right on that spot between daylight and I wonder what the temperature is like right at sunrise. I wonder if there's a point that you get, but you never get really warm though, do you? Very good. That's right. What was the one line in that movie that nobody could figure out what he was saying for the longest time? Burning out his fuse up here alone. Do you remember that? If you guys remember the song, there's a line that says, burning out his fuse up here alone. I remember as a kid, it took us forever to figure out what the hell Elton John was saying there. But I wonder, like, if you could live right on that periphery between the two as temperatures go. Any of y'all ever been to San Diego? Southern California? Obviously, that's what the map is down below. I love it. Oh, Coronado. Why were you in Coronado, Tim? For the Navy. Was it military training in Coronado? Oh, I got you. Yeah, I was stationed in San Diego in the Navy, so yeah, that's what Coronado, where all the aircraft carriers always tie up. Yeah, you would have to stand on that. I guess it would be a north-south equator. Okay, so if you've ever been to San Diego, my best friend, sorry, didn't get the last part. He was in the Army as well. Is that what you're trying to tell me? What were you training at the naval base for? Oh, EIT. Okay. What'd you do in the Army? Because I know the SEALs train out there. That's your MOS? What's it in real words? I don't remember all the. My dad was a career man in the Army. I grew up in the Army, but I don't. I know that number is your MOS, right? Ah, there we go. Ah, tanks. Love tank. Did you enjoy it? Yeah, me too. Me too. What I did enjoy, though, was I did love Southern California. The weather in San Diego is beautiful. During the day, it's not humid. It's what we call a Mediterranean climate. It's very similar to the Med. But during the day, it never gets real humid. The temperature never gets real hot. I traveled out there for SeaWorld a number of years ago, and I went in to go rent a car at the car dealership, and they said, well, what kind of car would you like? And I looked outside and said, give me a convertible. Drove around San Diego for a week. Of course, sunburned the hell out of the top of my head, but didn't realize that I should wear a hat, I suppose. But gosh, the weather there is fantastic. And if you look at the other temperatures around there, along the coast, Los Angeles, Santa Ana, Santa Barbara, they all stay relatively comfortable, 72, 75. But as soon as you move inland to like Palm Springs or San Bernardino, it gets hot really quick. The reason why is what I was explaining to you earlier about Florida. The proximity of the ocean. And let me tell you, folks, and Tim, I bet you're aware of this, the water out in California is a lot colder than it is here. Water in California in the Pacific stays about 68 all year round. It might warm up to 70 in the summer, but it's not like my wife and I always go over to Siesta Key every year. It's not like floating out in that nice warm water for hours on end. You jump in the water and cool off, and then you get back on the beach. The only people in the water typically are surfers, and well, I was in the Navy after we had drank enough, then we would splash around the water. But it's cold, okay? So again, the reason why this moderation occurs in this area right along the coast is because of the ocean. During the day, the sun comes up, the ocean heats up. So the oceans, those little, and all those water molecules in the ocean with their springs are bouncing as the sun is shining down on them. So the water is absorbing a lot of the heat. The land is too, but not as much. So San Diego stays nice and comfortable. At night, sun goes down. The water of the ocean then releases its heat, okay? And then the places along the coast get a nice, comfortable evening, right? However, inland in San Bernardino and the Palm Springs, you get into the desert climate. You get far away from the ocean that you don't get that regulation. So during the day, it'll be 106, and at night, like I said, on the desert, it can get really doggone cold, horribly cold. When I got out of the military, I wanted to stay in San Diego. I loved it so much. But man, I tell you one thing about Southern California, it's just immensely crowded. Gosh, even back when I was there in the late 70s and the early 80s, the freeways were 16 lanes across 8 lanes on either side. It's just really a hassle getting through town. Let me go back to that table slide. All right, I think we're still in the same thing. Yeah, we're still talking about the temperature moderation. Let's talk about this high heat of vaporization. Now, if you read in the explanation, what that basically says is that the same thing I've been saying all along. You're going to have to break a lot of those hydrogen bonds before water will evaporate, right? It resists changing state. Now, from a biological point of view, right, since we're applying this to biology, that allows you to maintain a constant body temperature. It allows you to maintain homeostasis. All right, heat of vaporization has a definition to it, just like calorie did, right? It's the amount of heat it takes 1 gram of liquid must absorb to be converted to gas. All right, and water has a high heat of vaporization. So what that means is as that water is evaporating off of the surface, it cools the surface. All right, as water molecules are evaporating off the surface of your skin, they're turning to gas, right? Liquid on your skin evaporates. When something evaporates, it turns to gas. When hydrogen bonds break, when liquid water becomes gaseous water, when hydrogen bonds break, they absorb the heat. What is the heat they're absorbing? The heat on your skin. You're hot. You've been out in the sun. The sweat on your skin as it evaporates, that chemical process of those bonds breaking when it turns into gas absorbs heat, takes the heat off your skin. It takes the heat off the surface of a sidewalk. It's not just a living organism. It takes the heat off anything. So it absorbs the heat, and for us, that keeps us nice and cool. Really neat adaptations of certain organisms that live in really hot climates. This is a picture of a Thompson's gazelle. African animal, right? Thompson's gazelles live in very warm climates, and they have to take an extra precaution to keep themselves cool, specifically to keep their brain cool. Why the brain? Well, I don't know, man. Think about it. If the brain goes haywire, you're screwed, right? So the brain is the important, really, and now the other organs are important too, but that brain is the big one. If you lose brain function, it doesn't matter if your kidneys and everything else is working. They're all controlled by the brain. So look at what the gazelle does. This is really neat. I don't have my pen on it. All right, artery, the carotid artery. Arteries carry blood away from the heart. So you see the arrow going towards the brain. Veins carry blood back to the heart. And if you go on into A&P, you'll learn more about that. But that's a definition. Artery carries blood away from the heart. Veins carry blood back to the heart. Notice as the carotid artery gets near the brain, there's that little net right there. What that basically means is that the artery branches out into little tiny capillaries, okay? And those little tiny capillaries are right next to the brain. And because of those little tiny capillaries, okay, I'm gonna throw something from lab in there yesterday, little tiny capillaries have high surface area to volume ratio, all right? Little tiny capillaries have high surface area to volume ratio. So as the carotid artery passes through that area, it then passes down into the nasal passages. Now it's going to go back to that area in just a second, but first that blood from the carotid artery is going to go down into the nose. And you see all of those capillaries in the nose, and those are all real thin, high surface area to volume ratio. If you wonder why does he keep saying that, things transfer faster when you have a high surface area to volume ratio. As the gazelle inhales, cool air passes over the nasal passages, passes through the nasal passages, excuse me, passes over those blood vessels, cooling the blood, and then the blood goes back to that little net part that you see there where it interacts with the brain. So the blood that is passed, so the blood that is passed to the brain is cooled off before it gets there. Maybe not a lot, but breathing in that air coming through those nasal passages. Again, remember I told you the other day that life, could have been my Bio 2 class I told this to, I'm sorry. Life is sometimes, the difference between life and not life is just maybe a couple of degrees, for example. So if you can cool the brain down a few degrees, that might be just enough. You don't have to make it refrigerator cold, but if the air temperature outside, and let's use Fahrenheit, right? The air temperature outside in Africa is 105. If the brain is 90, that might do it. That's probably still a little bit too warm, but you get the idea. Whoop, just dropped my mouse. All right. Isn't that neat? I love when Mother Nature does that kind of stuff and we investigate and we find out, look how they take advantage of that. It's just the neatest thing in the world. Any questions on that? All right, so that sums up basically those two parts of the table. The whole idea, let me go back again. Where are we? Oh, good. Perfect. So the high specific heat and high heat of vaporization. So read through those, and if you're getting lost in the mumbo jumbo, remember, bottom line, what those two properties of water do for living things is they moderate temperature. It takes a lot of heat to make water boil. Okay, so that means that you're going to absorb a lot of heat before that water becomes steam. And again, living things can't live off steam. We have to have liquid water. Okay, the next one down, the lower density of ice. What do you mean lower density of ice? Let's take a look at something here. Let me blow your minds for just a moment. All right, on the left is obviously a glass of iced tea. Looks pretty good. I love iced tea. My grandmother did too. One of my memories of my grandmother's walking around, and yes, Beth, that's right, walking around with a mason jar full of iced tea. That's why you get brain freeze. Yep, you eat ice cream, it super cools the blood vessels at the roof of your mouth, and then that cools off the blood in your brain, and your brain feels that. You know how to stop the brain freeze? Not stop, you can't prevent it. You know how to stop it or make it go away? Kinda. It's got neurons. So yeah, that'll work. Or warm it up. Drink something warm. Or what I'll do is I'll exhale over my mouth, so I warm up the roof of my mouth. But yeah, there's some people out there that never get brain freeze. Yeah, I had a couple of friends of mine that it just never affected them. I wonder if they're wired a little bit differently in their blood flow. Anyway, we're not talking about brain freeze here, but that is kind of cool. Yeah, I'm glad you made that connection there. But look at those two pictures side by side. The one on the left is, like I said, iced tea, and there's ice in there, and nothing looks unusual there. But on the picture on the right, it might look a little bit different. That's not water. That's actually liquid benzene. All right, benzene is an organic material. Where's my mouse? There we go. That's liquid benzene that you see in the beaker, and at the bottom, benzene. There we go. And at the bottom is solid benzene. Okay, let's go through and remember what we did in lab yesterday. One of at the very end of lab. What did we discover about things that are more dense than water? What happens to them? What happens if something has a density, greater than 1 gram per ml, okay? And if you have a density less than water, then obviously you float. So if you look at the picture on the left, ice is floating, so therefore its density must be less than the tea, the water that the tea is made out of, correct? That's a fair assumption. And we look on the right, and we see that, well, something's a little bit different there. The solid benzene is not floating in the water. Now, which of those two pictures looks most normal to you? The one on the left or the one on the right? And just kind of, stick with me in terms of normal. Like, what does he mean normal? In other words, if somebody brought you a glass of iced tea with ice and all the ice were on the bottom, you'd think that was a little bit weird if the ice didn't float, is what I'm trying to say. But if you think about it for just a second, Beth and Lindsay all said the one on the left, right? If you think about it for a second, that's a solid object, ice, floating in a liquid. Didn't I just say that solids have greater densities than liquids? Didn't I just say that state of matter depends on density? Solids have greater density, liquids have medium density, and gases have less. So in the picture on the left, that really isn't normal, right? It really isn't what we would expect. We would expect with the picture on the right. If you have solid water floating in liquid water, then you just like with solid benzene floating in liquid benzene in the beaker on the right, it ought to sink, right? But it doesn't. It doesn't sink. Isn't that weird? When you think about that, isn't that kind of strange? I mean, you've done it all your life. You put liquid in a glass and put ice and it floated. Nobody ever thought anything about it. But did you ever stand back for a second and go, that's weird? I remember Professor Clark telling me that solids have greater density. And ice is solid water. It's not liquid water. It's solid water. Y'all agree with me that that's weird? That ice floating is weird based on what we know? Bodies, to float, but they will sink. Human bodies? Yeah, they do. Typically, somebody asked me the other day about whales. Do whales sink after they die? High blubber content, high fat content in humans is going to keep your body floating for a while. And then once that decomposes and the heavier parts of your body become the majority, like your skeleton, then they sink. All right. Raymond, I'm not going to leave you waiting any longer. I'm going to tell you. The reason why ice floats, all right, the reason why solid water floats in liquid water has to do with, you guessed it, hydrogen bonds. All right, remember those hydrogen bonds that we saw as springs? And we said that when they get really hot, the springs start bouncing, and they absorb a lot of the heat, right? And when it gets too hot, the springs break and it becomes a gas. Okay, now we're going to go the other direction. We're going to cool off the water. So as you're cooling off the water water molecules, those springs are bouncing less and less. I wish I had the camera to show you my fingers, but you get the idea. They're bouncing, but they're slowing down as it's getting colder and colder and colder. Those springs are settling down and slowing down. And so look at this picture here. On the left, what we see is liquid water, and you can see that the dashed lines are the hydrogen bonds, and it's telling you that in liquid water, those bonds are springy. They're moving. Now, if it's really cold liquid water, they're not springing much, but they're still moving. Here's something that's unique about water. Because of the hydrogen bonds, because of the way those hydrogen bonds work, when you cool water down to about 4 degrees Celsius, let's review for just a second. At what temperature Celsius does water freeze? That's Fahrenheit. 0. So 4 degrees Celsius is liquid, right? It's not a solid. All right. When you cool water down to 4 degrees Celsius, at that temperature, water has its greatest density. Water's at its greatest density at 4 degrees Celsius. Very cold water. Where is the cold water in your pool? Where's the cold water in a pool? Top or bottom? Right, because it's heavier. So 4 degrees Celsius water, which is pretty doggone cold. I wouldn't want to be swimming in that stuff. Is at its greatest density. Oh, well, it's not frozen yet. So got 3, 2, 1, and 0 to go. As water cools off from 4 degrees, those hydrogen bonds stop being springy and they become rigid. Not only do they become rigid, but they line themselves up in a very set pattern, a very set distance. What you see down below there, 4.48 and an A with a little 0 over the top, that's a really, really, really small metric unit that we didn't even introduce yesterday. That's called an angstrom. An angstrom is smaller than a nanometer, smaller than a nano. So we're talking down at the molecular level here. When water molecules freeze, when water becomes from liquid to solid, those water molecules are getting closer and closer and closer together. After 4 degrees, they actually start pushing apart, and at 0, they set up this rigid crystal structure with every molecule about 4.5 angstroms away from one another. Now, what has happened from 4 degrees, where the water molecules were at their greatest density, when they were closest together, is the water molecules, as you cool them off further, begin to push out. All right? Density increases as you cool it off. So you get to 4 degrees, the water molecules are as close as they're going to get. Now you keep cooling it off. 3, 2, 1, 0. The water molecules actually go opposite. They start expanding out because they're going to make this crystal structure. It's because of the hydrogen bonds. Now, because that ice then expands out just a little bit, that means its density decreases. So in liquid water, solid water can float because it's unique, because of the hydrogen bonds, in the sense that they actually decrease the density of the water as you cool it off from 4 degrees to 0 degrees. And again, I keep saying 4 degrees because we say about 3.98, but 4 degrees Celsius is the maximum density of water. Isn't that cool? Never knew that, did you? So think about water molecules getting close together. At 4 degrees, they're as close as they can be. And then once you get colder than that, they actually push apart a little bit. All right, that's the chemistry, that's the physics. Why do we care? Well, for one thing, I like having the tea floating at the top of my ice. Yes, that's exactly right. That's exactly right. You put a bottle of water into the freezer. If you filled it all the way to the top and put the top on, it'll explode. Yeah, did I say that? Well, I like to have the ice floating at the top of my tea, only because it looks normal to me. All right, couple of things, though. When lakes freeze, they freeze at the top, don't they? They don't freeze all the way through. The reason why that is because the ice that's forming in the water as it's getting cold outside floats to the top. It doesn't sink to the bottom. That means that during the winter, the shrimp you see on the left, and that's a sea anemone and a sea star on the right, they're under ice. They can live in those conditions. So even though it gets winter and the lakes freeze over the top, the critters down below are still living in liquid water. That shrimp couldn't survive in solid water, right? Couldn't survive in ice. It would die. So this ice floating at the top, because of that physical property, allows life to continue in these water ecosystems until spring comes, or forever, depending if you're one of those organisms that lives down there where there's permanent ice. If you're thinking, how does an organism survive there? Well, there are even organisms that can photosynthesize under the ice. There's not a lot of light, but there's enough. You can see in that picture on the right, a little light coming through. The freezing also provides insulation. So, for example, if the air temperature outside gets well below freezing, the water temperature below the ice will always stay about the same. That's why, if you see the picture on the lower left, people that raise orange groves, if a freeze is coming in Florida, they'll turn the sprinklers on to their orange trees, won't they? They want the freeze to form because that means that that temperature next to the orange is never going to get any colder than 0 degrees Celsius, even though the air temperature might. And again, if the air temperature outside gets, say, -2 degrees Celsius, even though it's only 2 degrees, that could be the difference between your crop being destroyed or not. Don't some freeze in ice until? Yeah, some do. Some critters do. Yeah, you gotta have a very specialized physiology to survive that, though, because unfortunately, when you make those ice crystals, they're very sharp. That's what frostbite. That's what it does to your skin. The liquid in your cells freezes, and it forms those solid crystals, and they're very sharp, and they just destroy cells. That's what causes you to lose that tissue. But whenever critters do that, they have to have some reason to deal with that. And a lot of critters that live in cold climates, was it you guys or my bio 2 I was telling you about, they actually have a little bit of antifreeze in their blood. Not Prestone. They didn't go down the road to Lowe's buy some Prestone, but they have a material in their blood that acts like antifreeze. The picture of the husky doesn't have anything to do with other than I think it's a cool picture. I love huskies. I love the look on his face. You know, he's kind of like, I shouldn't be walking here, but I am. You know, I wonder in a dog's mind if they're able to process, you know, I'm walking on water. Because it looks like he's got a little bit of trepidation. Yeah. Hopefully the ice is thick enough, right? Huskies, they're neat animals. Very interesting critters. All right, let me go back. How much time we got? We got a little bit. What's easy? There we go. So we've done cohesion, temperature moderation, solubility. Water is what we call a universal solvent. All right. Now, a little bit of terminology here, or did I? Oh, I did it. I did it on the slide, so I need to type it in here. Go back to the slide. When we talk about solutions, solutions are made up of two parts. Solutions are made up of what's getting dissolved, that's the solute. Solutions are made of what's doing the dissolving, that's the solvent, and then together they're the solution. If the solvent is water, then we call it an aqueous solution. If the solvent is something else, then we don't call it an aqueous solution. So for example, in the picture on the right, if we're dissolving, was that salt? Yeah. If we're dissolving a salt crystal in water, then what we're doing, the solute is the salt, the solvent is the water, and then the solution is the saltwater solution. All right, now how does the solubility work? What happens in a solution is that the solvent dissolves the solute. All right, I'm not saying anything too weird there, right? You know, you stir in salt into water and it dissolves. That's what it does. We say it's dissolving. All right. If you look at the picture on the right, you can see, for example, in the case of the salt crystal, how that happens. When the salt is dumped into the water, it dissociates. In other words, the ions disconnect. The positively charged sodium, the negatively charged chlorine that are held together by magnetism, basically, disconnect. And all those water molecules, which are much better connectors, much stronger magnets, if you will, then begin to surround. And notice the sodium that's positively charged. Look at what end of the water molecule is attracted towards it. You see that? It's the oxygen end, right? And for the chlorine that's negatively charged, it's the hydrogen part. So what those water molecules do when they dissolve the salt crystals, they swoop in and they basically pull on those ions until they start separating them. See, the pull of all those water molecules is greater than the attraction between the sodium and the chlorine, so it begins to separate them. They begin to dissolve. That's what we mean by dissolving something. That's what we mean by something being a solvent. What we mean by water being a universal solvent is we say that water will dissolve most everything. Okay? Water will dissolve most everything. Now, why is that important for living organisms? When we get into talk about cells in chapter 6, we're going to talk about the cytoplasm of the cell, the liquid filling of a cell. Everything that goes on in a cell, everything that's all those life functions that go on in a cell, all occur in a soup, basically, a liquid soup. It facilitates or makes it easier for things to move around. Remember all the chemical reactions that I've been talking about that living things use? Atoms and molecules can't think. They don't know that they're supposed to combine. The way that the cells get them to do that is, for one thing, you put a lot of them together, you let them randomly move around in that liquid part of the cell, which they can do very easily because that's what solvents do. Solutes can move around in that liquid portion of the cell, and it increases the chances they'll come into contact with one another. Right, now we'll talk a little bit more on that when we get into enzymes. But the important part of the water here is to provide this mixing medium, right? It's like a social lubricant for solutes, right? It allows them to dissolve and to spread out. When ions are dissolved, what we end up getting are hydration shells, which are basically water molecules surrounding each of those ions. That's what we mean by a hydration shell. Now, this can occur with ions, this whole dissolving thing, things that aren't typically charged, like large proteins. Proteins may have some charged areas to them. You can see in the little inset, that's what's happening there. Now, if I put water and oil together, would the water molecules be able to dissolve the oil? Why not? I know one's polar and one's non-polar, but kind of looking at this picture here in the previous one, why do the water molecules have no effect on the oil? Not density. They would separate by density. Yes, you're right, guys. But I mean, they were mixed together. The bonds in the oil, you're saying, Tim? Okay, oil is nonpolar, right? Nonpolar things don't have positive and negative ends. So if oil was dissolved in water and water's got these positive and negative ends to it, there's nothing for it to attach to. Think about it, taking a magnet and putting it on your shirt. Won't work, will it? Doesn't stick. When you emulsify oil, what you basically do is break it down into smaller and smaller and smaller droplets. You don't ever really separate it. You don't ever really turn it into something that's not oil. Emulsification just makes smaller and smaller drops. When the oil spill occurred out in the Gulf, the Deepwater Horizon, you remember what they did is they sprayed, among the things they did to try to get rid of the oils, they sprayed dispersant. You remember they were talking about that? Some folks were actually saying that the dispersant is worse than the oil. Well, then BP comes up and says, oh, look, we sprayed dispersant, no oil is here. Scientists and people who know better realize the oil is still there. The dispersant is an emulsifier. The oil is there. It's just little tiny droplets and it's spread out more and you can't see it. It's still going to affect the environment. It just looks pretty. Thank you, BP. Okay? Any questions on that? All right, I got one more slide and then I'll be done for the day. I want to finish this up because it fits right in with this thing we've been talking about, oil and water and not mixing and all that sort of stuff. Substances out there in the world are either hydrophilic or hydrophobic, okay? And hydrophobic substances like oils and waxes and fats, they don't dissolve in water. They're afraid of water, right? They have no affinity for water. Things like vinegar, acids, bases, ammonia, sulfur dioxide, hydrogen sulfide, that rotten egg smelling gas, all those things are hydrophilic. They will dissolve in water. Remember I said yesterday like dissolves like? So hydrophobic substances will dissolve in other hydrophilic substances will dissolve in other hydrophilic, right? No questions on that. Now, there are molecules out there in the world that live a dual life. They're amphiphiles. Now, amphi means both, like an amphibian. Amphibians live in the water and on land. And a philic is to love. Like Philadelphia is the city of brotherly love, right? Or if you're a bibliophile, you love books. Amphiphiles have affinity for both. They have an affinity both for hydrophobic and hydrophilic substances. Your laundry detergent, that's how it works. The dirt on your clothes is usually oils, right? And it's hydrophobic. So when you put it into the washing machine and you add water, if you didn't put in detergent, nothing would happen. The water, as we just said, would never get the oil and the dirt off your clothes. You need to add one more thing. You add the detergent. And detergent, the molecules of Tide have parts of them that are hydrophilic and parts of them that are hydrophobic on the same molecule. So the hydrophobic parts of the detergent molecule are attracted to the oil on your clothes. The hydrophilic parts are attracted to the water that's in the washing machine. And after the agitation cycle, when the water is drained away, the water that's leaving drags the detergent molecules with it. The detergent molecules that are leaving, because the water is leaving, are dragging the oils with them. Right? That's how you get the oil off your clothes. Now, a little bit later on in subsequent chapters, we're going to look at a molecule that you see there, and I'll talk more about what that molecule is. But that molecule I introduce you to is another example of an amphiphile molecule. It's got a hydrophilic head, and it has these two hydrophobic tails. This is called a phospholipid. Don't write that down and don't worry about it right now because we will discuss it later on, but I just kind of want to make a little connection. What does they call that? Foreshadowing in literature. Talk about something we're going to talk about in the future. Okay, so that's good. We only have a few slides left in this chapter. We'll be able to start on chapter 4, or well, Tuesday we'll finish up the couple in 3 and then start on chapter 4. So that's all I have for today. If y'all have questions, by all means, please stick around. If not, please have a good weekend. Have a good holiday weekend. Remember Tuesday online, and remember Wednesday lab number 2 and on campus, okay? Let me know if you have any problems, any concerns. If you're working on your assignments over the weekend, as I said, please, by all means, go ahead and email me. I won't be doing much over the weekend, hopefully. Thank you. I appreciate it.